Okay, so let's see, let's get through this. So we did some examples in the last video with the calculating the wavelength. We're calculating the frequency. I think there's only really one other equation, if I'm not mistaken. Some of this stuff we just don't have time to do. There's calculations you can do with this kind of, where the object is, where the image is, and things like that. We're not going to do that. So I'm kind of skipping. Very briefly, I'll talk about this is an example of the wave nature of light. When light, or any wave really, encounters two small openings, what's going to happen on the other side of the two openings is there'll be what's called interference. So this is an example of interference. And only light does this, or sorry, only waves do this. Okay, so yeah, we just talked about that. Here's another example when you have basically light is unpolarized generally. That is, it's waving back and forth in all directions. And then if you have a filter, it'll block all the directions for, in this particular example, except for up and down for the way we're looking at it. So that's what we mean. So this is showing it as well. So here comes unpolarized light. It goes through the filter. It's only gonna allow up and down through. And so if there's another filter or another Polaroid, as they're called, here's an example. Light's unpolarized. It comes through only up and down. Light gets through. And then if you have another filter at 90 degrees, you won't have any light getting through. So that's also a wave-like behavior for light. Let's skip that. And then there's particle behavior. This is a discovery of Planck, Max Planck, in the year 1900. Made this great discovery, and this is really the beginning of quantum mechanics. So what it says is the energy of a single photon, so now we're talking about the particle-like behavior of light, is equal to a constant. Later it was called Planck's constant. This is a constant in the universe, just as important as the speed of light. Its value is 6.63 times 10 to the minus 34th, and its units are joules times seconds. And then that gets multiplied by the frequency of the light. Okay, actually, so there's two more equations. So there's this one, and there is, so the photoelectric effect actually is what won Einstein the Nobel Prize. His theory of relativity was too controversial at the time. But what the photoelectric effect does is it shows light acting like a particle and not a wave, and it can only be explained if light acts like a particle. So it turns out light acts, let's skip this, light acts as both a particle and a wave. Sorry. It doesn't have the other equation, sorry. There is one more equation. Let me, I'll write that out. So let's do an example. So the energy of a photon is the Planck's constant times the frequency. Okay, so let's say we had, we'll do a full example here. Suppose I had a photon of wavelength, I don't know, how about 400 nanometers. To just go back and kind of review the other stuff. If we had a photon of that wavelength, then we have to in order to figure out the energy, we have to know what the frequency is. Okay, and by the way, the energy is going to be in joules, and the frequency is going to be in hertz, and Planck's constant is what it always is. So it's 6.63 times 10 to the minus 34th. It's an extremely small number, 34th, and its units are joules times seconds. Okay. All right. So what we have to do is from this wavelength, we have to figure out the frequency, and then we're going to plug the frequency into this equation to get what the energy is of a single photon of that particular wavelength. All right, so it's pretty simple to figure out the frequency. That's the speed of light divided by the wavelength. So it's 3 times 10 to the 8th meters per second. And we just did this in an earlier video. And of course this is 400 nanometers, which we know is 400. I'm just going to use my metric prefix times 10 to the minus 9th meters. Okay, so we have to use that. So it's 400 times 10 to the minus 9th meters, and the meters cancel, and you get 1 over seconds, which is hertz. So here, let me gotta find my calculator. Let's see. What the? All right, so when you do this calculation for the frequency, you get 7.5 times 10 to the 14th, and so the energy of that photon is going to be Planck's constant, there it is, times this particular frequency. And notice the the frequency is in hertz, which is 1 over seconds. That cancels these seconds right here in Planck's constant, and so the energy that I get when I do this is about 4.97 times 10 to the minus 19th joules, which is an extremely small amount of energy. So let's write that out. 4.97 times 10 to the minus 19th joules. And I got a couple of things to say about this before we end this video. This is actually the end of the chapter. This is the last equation. I was thinking of something else when I mentioned that earlier. And this, notice this times 10 to the minus 19th joules. In the next chapter, not this chapter, but in the next one, chapter 8, we're going to use what are called electron volts, extremely small units of energy, and so we're going to convert between joules and electron volts. So just be prepared for that. All right. So that's the energy of that particular photon. Remember, another thing I guess I should say is, suppose you'd had something that was here's another example. So let's say this is a second photon. We'll call this E2. Or EB, let's call it EB, not to. All right, so if this one was EA, and this one was 4.97 times 10 to the minus 20th joules. What I want everybody to realize is this, of course, even though they numerically are almost the same. But this, since it's minus 20th, that's a smaller number. So that means EB has a smaller energy than EA. So EB, the energy in photon B is smaller than the energy in photon A. And similarly, if we had another one, let's see, I'm running out of, if I had another one, EC, and it was exactly the same numerical value, 4.97, I'm just making this up, times 10 to the minus 18th joules, then of course that has greater energy than even EA, right, because it's times 10 to the minus 18th. So EC, let's see, this is an A, EC has the greatest energy. So just a little comparison between energies there. All right, and that's the end of Chapter 7.